Let's talk about capacitors. Okay, so capacitors are devices that consist of two conductors that are separated by a distance, and each of the conductors hold an equal and opposite charge on it. Okay, so for example, suppose you have a spherical shell here and a spherical shell here. Okay, and suppose this has some charge Q on it, this has some charge minus Q on it. Okay, then this would be considered a capacitor because it's two conductors separated by some distance. So this is R1, this is R2, and they're holding an equal and opposite charge on them. Okay, you can also have a cylindrical capacitor, for example, an inner cylinder here and an outer cylinder here. Okay, this one carrying some Q on it, and this one's carrying some negative Q on it. Okay, and this is the separation between them. So that's another possible capacitor you can have. Two plates, okay, separated by some distance D. Okay, this one having some charge Q, this one having some negative Q. So that would also be a capacitor. Okay, how much charge a capacitor holds depends on how much voltage is applied across its plates. The proportionality constant between the charge and the voltage is called capacitance. So capacitance of a capacitor is found using this formula, Q equals CV. Okay, so for any capacitor, the capacitance depends on geometrical factors only. Okay, if you have a spherical capacitor, it's only going to depend on the geometry of the sphere. If you have a cylindrical capacitor, it'll only depend on the geometry of the cylinder, or if they're parallel plates, then it should only depend on the geometry of those plates. Okay, so for this case, let's work out what the capacitance is for a spherical capacitor. So Q in this formula means the Q on one of the conductors, okay, and this is always positive. So this is absolute value. Capacitance is also always positive, and the potential difference is also positive. Okay, so what is the V between R1 and R2? Okay, so we know that since these are conductors, the potential at R1 is going to be K times Q over R1, and the contribution of the outer one is going to be negative KQ over R2 because you're inside that. And at R2, the contribution of the inner sphere is going to be KQ over little r, which, since you're at the surface of the outer sphere, little r becomes capital R, and the contribution of the outer sphere is KQ over R2. So this becomes 0. So the potential difference is KQ over R1 minus KQ over R2, absolute value. Okay, so this becomes Q equals C times this V that we just found, VR1, because VR2 is 0. Okay, so capacitance is equal to, Q's cancel, so it ends up being 1 over K over R1 minus 1 over K over minus K over R2. Okay, so that's the capacitance for a spherical capacitor. Okay, now let's move on to capacitors in a circuit. Okay, so suppose you have a battery. So this is the positive terminal of the battery, this one is negative, and it's connected across a capacitor like this. Suppose the value of the battery is V, and the capacitance of this capacitor is C. Then to find the charge on this capacitor, you would use the formula Q equals CV, and that will give you the charge. And what this charge would mean is that this plate has some positive Q on it, and this plate has some negative Q on it. Okay, so that was a very simple case. Suppose now you have the case when you have two capacitors connected like this across the battery. Okay, so this is V, and suppose this is C1, and suppose this is C2. And suppose we're interested in finding the voltage and the charge across C1, charge on C1 and C2. Okay, so here the charge on C was Q, and the voltage was the voltage of the battery. So how do we find it here? Well, we don't know how to solve this problem. We know how to solve this problem. So we can make this problem into the simpler problem by simplifying the capacitors into a single capacitor. So this is going to be your battery voltage V, and this is going to be some equivalent capacitance. Okay, so then across this capacitance, we know that Q equals the capacitance value times the voltage. Okay, but that's the case across this capacitor. That's the combination of these two together. What about the charge and voltage on each one separately? Well, for this, we have to use the principles of circuit theory. Okay, so since this is a circuit, we know that voltage across each of the components is gonna fall, and the sum of those voltages is gonna equal the voltage of the battery. So V of the battery is gonna equal the V across C1 plus V across C2. Okay, another thing about series circuit is that when you have capacitors in a series circuit, the charge is the same everywhere. Okay, so this C1 and C2 are going to have the same Q. Okay, but what is going to be the value of that Q? We have to find that. Okay, so Q is same in a series circuit. Okay, so with this information, we can find the charge and voltage on C1 and C2. Okay, so we know that V is equal to, from this picture here, Q over the equivalent capacitance. Okay, and V1 is equal to Q over C1, and V2 is equal to Q over C2. Okay, so Q's cancel. And we're left with 1 over C equivalent plus 1 over is equal to, 1 over C1 plus 1 over C2. Okay, so this is how you find the equivalent capacitance of capacitors in series. So if you had n of them, so you would keep adding the contribution of each of the capacitors and then find your C equivalent. Okay, so and then once you know your C equivalent, you can find what this Q is going to be. Okay, and then once you know your Q, you know that V1 is equal to Q over C1 and V2 is equal to Q over C2. Okay, so that's how you find your voltages and charge on C1 and C2 for a series circuit. Okay, and these are the things to keep in mind, that voltage of the battery is equal to V1 plus V2, charge is the same everywhere, and the equivalent capacitance of a series circuit is found by this formula. Okay, now let's look at capacitors in parallel. Suppose you have a capacitor here and another capacitor connected in parallel. And same thing, you have to find the voltage across C1 and C2 and the charge on each capacitor. Okay, so again we have to use circuit theory here. Okay, so since these two capacitors are connected in parallel across the battery, they're going to have the same voltage across them. So in a parallel circuit, the voltage across parallel branches is the same. Okay, but charge is different now. Okay, so sort of the inverse of what we had previously, right? Charge was the same in a series circuit and voltage was different. So here, it's the opposite. So then that means that C1 is going to have some Q1 on it, and C2 is going to have some Q2 on it. What is going to be the voltage across C1 and C2? Okay, since they're directly connected across the battery, they each are going to have the voltage of the battery across their terminal. Okay, and the Q is going to be so that the Q supplied by the battery is equal to the charge on one capacitor plus the charge on the second capacitor. Okay, so same thing. This circuit you can replace by a simpler circuit having the voltage of the battery and some equivalent capacitance that we don't know. Okay, and then this is going to have some charge Q on it, and the voltage is going to be the voltage of the battery because that's the only voltage source. Okay, so and these two Q's are the same. Okay, so this Q is equal to equivalent capacitance times voltage. Q1 is equal to, Q1 is this one, is C1 times voltage, and Q2 is equal to C2 times voltage. Okay, so voltage cancels, so equivalent capacitance is equal to C1 plus C2. And if you had, any number of capacitors in parallel, you would keep adding them like this to find your equivalent capacitance. Okay, so once you find your equivalent capacitance, then the Q is going to be your capacitance times the voltage. Okay, so this demonstrates how to find the equivalent capacitance for a parallel capacitor network. And Q1 specifically is going to be C1 times the voltage of the battery, and Q2 would equal C2 times the voltage of the battery. Okay, so we found everything that we were interested in on this parallel circuit. Now let's look at a case that's slightly more complicated. So suppose there's some C1 here, C2 here, C3 and C4. Okay, like this, and same thing. We have to find the charge and the voltage across each of these components. Okay, so what we have to do is, we have to get it in the form where we only have one C equivalent, and then from that we're going to work backwards to find the Q and voltage across each of these components. Okay, to start simplifying this circuit, we're going to simplify C3 and C4 into a single series combination of capacitors. Okay, so it becomes C1, this becomes C2, so nothing changes here, but these we're going to combine into an equivalent capacitance. Okay, so these become some C equivalent of 3 and 4 together. So this is still V. Okay, and then we can simplify this more. We see that C2 and this combination of capacitors is in parallel together. So this becomes C1 and C2 in parallel with C3 in series with C4. Okay, so we're calling this equivalent capacitance of C3 and C4 C3 plus C4. Plus meaning they're in parallel, and plus meaning that they're in series, and this parallel sign means that C2 is in parallel with the second component. Okay, so this becomes this, and then we can simplify this more. So we see that C1 is in series with this capacitor, so it becomes a single capacitor. Okay, where C1 is in series with C2, where C2 is in parallel with C3 plus C4. Okay, so now first of all, let's find what this capacitance is. This is the final equivalent capacitance. Okay, so this is different from this equivalent capacitance. So for this, what you're going to do is, to find the equivalent capacitance of C3 and C4, you're going to say, let's see, how do we do this? Okay, so let's just do it here. So 1 over C equivalent for C3 and C4 is going to be 1 over C3 plus 1 over C4. Okay, then to find C2 parallel with C3 and C4 is going to equal, you would simply add C2 to this. Okay, so it becomes C2 plus, okay, so let's call this equivalent 1, let's call this C equivalent 2, okay, and then let's call this C equivalent final. So this is C equivalent 1, forget this, okay, and then C equivalent 2 is going to be C2 plus C equivalent 1, and then the final equivalent is going to be one over C equivalent 2 plus 1 over C1. Okay, so instead of saying 1 over C equivalent equals 1 over C equivalent plus 1 over C1, we just flipped this. We said C equivalent is equal to 1 over the whole thing. Okay, which is valid. Okay, so we know what C equivalent final is. So from this we can find that the Q on this whole capacitance is going to be the equivalent C capacitance on the equivalent final C capacitance times the voltage of the battery. Okay, so now since these capacitors, this one C1 and the second equivalent capacitance are in series, then they're going to have the same charge, okay, which is going to be this charge. So we found the charge on each one. But what about the voltage? Okay, so if you know the charge, then the voltage across C1 is going to be Q over C1. Okay, so then that's it for C1. We know that the charge across C1 is Q and the voltage is V1, so we're done with C1. Okay, so C1 has been found completely. Okay, what about this second one? We know that the voltage across the equivalent capacitance for the second equivalent capacitance is going to be Q over the second equivalent capacitance. Okay, so we found, so this gives us the voltage across, this capacitance, this equivalent capacitance. And then we know that this capacitor is a combination of these two capacitors. Okay, and since these two capacitors are in parallel, then that means that the voltage across them has to be the same. Okay, so the voltage across this capacitor is the voltage across each of them. Okay, so the voltage across C2 is going to be, what we just found is the voltage across C equivalent 2. Then charge on C2 is going to be C2 times V times the voltage across the equivalent capacitor that we just found. So then this Q is different from this Q, okay? So, and then that's it for C2. Okay, we found the charge on C2 and we found the voltage on C2. Okay, so now we're left with C3 and C4. So we know that the voltage across the equivalent combination of these is this voltage, okay? this voltage that we just saw. So that means the charge across this capacitor, charge on this capacitor is going to be C equivalent 1 times voltage across the equivalent capacitance of the second combination. Okay, so this charge is going to be the charge on each one also because they're in series. Okay, so this C3 is going to have some, so let's call this Q double prime. It's going to have some Q double prime on it, and C4 is also going to have some Q double prime on it. Okay, so then if we know that the charge on C3 is Q double prime, then the voltage across C3 is going to be Q double prime over C3, and voltage across C4 is going to be Q double prime over C4. Okay, so that's everything. We found that charge on C1 was Q and the voltage is V1. We found that the charge on C2 was Q prime and the voltage across C2 was VCEQ2. And then we saw that the charge on C3 and C4 was Q double prime, and these are the voltages across C3 and C4. Okay, so first we worked forward and then we worked backwards, to figure out what we wanted. Okay, so we discussed capacitors and circuits. Now let's discuss a little bit about dielectrics. Okay, dielectrics are insulating materials that you can insert into a capacitor, and what it does is it increases the capacitance. Okay, so if your capacitance original capacitance is suppose C1, then after you insert the dielectric, it becomes kappa times C1. Okay, where kappa is the dielectric constant and C1 was the original capacitance. Okay, so essentially, so suppose you had a capacitor and this one had some positive charge on it, and this another capacitor that has some negative charge on it. Okay, so then we're saying that the initial capacitance of this capacitor is C. Okay, because there's electric field lines between the two plates. Okay, what happens with the dielectric is that you have your positive plate and you have your negative plate, and you insert in some actually let's do a side view. Okay, suppose you have one plate and another negative plate here, and you insert in some dielectric material. Okay, then it's gonna form dipoles that look like this inside this insulating material. Okay, plus charges are going to be attracted to the negative plate, and the negative charge is going to be attracted to the positive plate. Okay, and then these are going to cancel each other. Okay, but the ones that are on the edges are going to create their electric field that points in this direction. Okay, so this electric field is going to be opposite from the direction of the electric field that was being created by the plates of the capacitor that was going like this. Okay, so essentially what happens is, your electric field decreases with the dielectric in. Okay, so now suppose that you have, a battery that's connected to a capacitor. Suppose this is some C. And then, so initially, the charge on this capacitor is going to be C times V. Okay, then what you do is, your capacitor is still in the circuit, but now you insert in some dielectric material. Okay, so the capacitance becomes kappa times C1. Then what is going to be the charge on this capacitor? Charge would be the capacitance, which is kappa times C1 times the voltage. Okay, but what happens if, suppose you had the capacitor like this, and then it has some charge Q on it, and then you removed it from the circuit. Okay, so this is your C, and then you insert the dielectric in. Now what is going to be the voltage across this capacitor? So you know that this plate had some Q on it, and this has some negative Q on it. Okay, so with the dielectric, is this charge going to go anywhere? Well, it doesn't have anywhere to go. So this is going to be the charge on the plates once you insert the dielectric in. Okay, and then we know that the capacitance just simply becomes kappa times C1. Okay, so, but something has to change to take into account the fact that capacitance has changed. Okay, and the way that happens is your voltage becomes different. Okay, so your V prime on the capacitor in this case is going to be Q over kappa times C1, which is your old voltage divided by kappa. Okay, so in this case, when you disconnect the battery, your voltage drops by a factor of kappa. In the case when you have the battery connected to the capacitor, your charge increases by a factor of kappa. Okay, so that's a little bit about dielectric. So last thing is energy in a capacitor. Okay, so you know that we discussed that potential energy is Q times the potential difference. Okay, so the energy on the capacitor you can find using the formula integral of dq, each of the charge that you're going to be moving from one plate to another, times the potential difference. Okay, and then you know that V for a capacitor is Q over C dq. You're going to integrate from 0 to the total charge. So it becomes Q squared over 2C from 0 to Q. So it becomes Q squared over 2C. Okay, and then for the capacitor, you know that from this relation, you know that Q equals CV. So if you substitute in CV, it becomes C squared V squared over 2C, which becomes 1/2 CV squared. Okay, so that's another relation for energy that you can use. And then you know that CV is equal to Q, so you can also rewrite this as 1/2 QV. Okay, so this formula can also give you the energy of the capacitor. Okay, one comment about the energy of the capacitor. So we found that the energy of the capacitor is equal to 1/2 QV. But why this 1/2? Why not just Q times V? Okay, because that would give you the energy, right? Voltage times the charge, that's what we've been saying. So to understand that, let's look at what happens in a capacitor. So suppose this is positive plate, this is a negative plate. Okay, and there's electric field in this region because of the charges that are on the plate. Okay, now suppose you connect the positive plates and the negative plate. Okay, so then as these positive charges go from the positive plate to the negative plate, they're gonna be canceling the charge that is of the opposite sign. So suppose this charge goes from here to here, so they cancel each other out. Now look how much charge is left. Okay, only 2 positives here and 2 negatives here. Okay, so because the charge decreased, then so did the electric field, and so did the potential difference. Okay, so then this charge doesn't have to go through as much potential difference as this one did. Okay, so this one goes from here to here, then it cancels this one. Okay, and then this charge, is the only one that's left over. Then it hardly has to go through any potential difference, and it just goes from this plate to the other plate. Okay, so this was just a symbolic example showing these 3 positive charges. but it explains the concept that as charges go from one plate to another, the potential difference is decreasing. So you cannot just say that Q times V, because V is not constant. So that's why in that formula, when we said that E is equal to integral of dQV, if V was constant, we could have just pulled it out of the integral and said that E is equal to Q times V. But that's not the case. V is constantly changing because E is proportional to how much charge is on the plates, and voltage is proportional to the electric field, right? Because voltage is electric field times distance. So if the electric field is decreasing, so is the voltage. That's why you cannot pull it out of the integral. And when you take into account, the whole discharging of the capacitor, then it ends up being one half Q times V. Okay, it just happens that this factor is 1/2. So that's why this factor of 1/2 is here. Okay, so that was just a comment that I wanted to make. So that concludes capacitors. If you have any questions, please leave a comment. See you in the next video.